Welcome to our Unit 5 instructional video. We're going to start with introduction, and in this unit, we're going to talk about combinatorics concepts. What are the combinatorics concepts? Well, in many probability problems, the big obstacle is finding the total number of outcomes. And in this section, we're going to present several methods for finding such numbers without directly listing and counting the possibilities. But we're going to start with what is called a tree diagram. The tree diagram actually organizes our counting techniques, and we're going to first look at this tree diagram, and then we're going to come up with the rule that will help us develop, which will help us find the number of possibilities without actually listing all of the possibilities. Let's consider the following example. We're gonna flip a coin 3 times in a row, and we're gonna we need to write a sample space for this procedure, meaning list all possible outcomes. If you haven't seen a video on sample space, please do so. All right, so we're gonna start with 1 point. And then we're gonna create or draw a branch for each possibility, with each possible outcome. So we're gonna list all possible outcomes for the first flip of a coin. So we have 2 possible outcomes. We're gonna either get heads or tails. So we're gonna draw 2 branches, one outcome for heads and one outcome for tails. Now let's say that we flipped the coin 1 time and we got heads. What are the other possibilities? What are the outcomes for the next flip? Again, we have 2 heads or tails. Now, if we got tails on the first flip, we still have 2 possible outcomes for the second flip, and those are heads and tails. So we describe the possible outcomes for the first flip of a coin and the second flip of a coin. We're going to continue in the same manner to describe the outcomes for the third flip of a coin. So if we got heads on the first and heads on the second, we still have 2 possible outcomes for the third flip, heads or tails. And if we got heads on the first and the tails on the second, we still have 2 outcomes for the third, being heads or tails again. Okay, so same principle to this branch. So we still have heads or tails, or heads or tails. Now this tree diagram describes all possible outcomes. So we could, for example, now we can use it to list all of the outcomes. So heads, heads, heads. Or heads, heads, tails. Or heads, tails, heads. Or heads, tails, tails, and so forth. And the right branch of this tree diagram, we've done that before. So we're gonna have a total of 8 outcomes. And if you count the number of in the last branch, the number of branches in the last row, you're gonna get 8 branches. So, and that equals the total number of outcomes in the sample space. Now, Our goal in this section is to be able to predict how many outcomes we're going to have in a sample space without actually doing a tree diagram. So think about that goal as we're going to look at the next example. And in the next example, we're going to do the same thing. We're going to do a tree diagram. So here's our example. It says Ramona has designed 4 tops, 2 jackets, and 3 pairs of pants for her fashion show. How many different outfits can she create? And we're going to assume that any top goes with any jacket, goes with any pair of pants. They're interchangeable, so there are no limitations there. And how many different outfits can she create? So I'm going to use first letters. I'm going to use colors to identify, the tops, jackets, and pants. So for the tops, I'm going to use purple, red, beige, and yellow. So this is our tops. Now for jackets, I'm going to use aqua and orange. So this is jackets. And for, 3 pairs of pants. So I just need 3 colors. So the reason I pre-selected colors because I'm going to only use the first letters of each color to identify the color, and I wanted them all to be different letters. So here we go. So again, we're going to start with 1 dot. And then and then a branch for each possible outcome. So first we're going to select the top. And so we have 1, 2, 3, 4 different possibilities. So that will be reflected in 4 branches. So 1, 2, 3, and 4. And I'm going to label the colors purple, red, beige, and yellow. Okay, so once we selected each top, we then have 2 possibilities for jackets. So out of each, I'm going to draw 2 branches. And so if I selected, let's say, the purple top, I can still match it with aqua or orange jacket. So aqua or orange. Same for if I selected the red top, I still have the choice of aqua or orange jacket, and same for the rest of the jackets. Now, once I've selected the pants, I mean, tops and jackets, I need to select pants, and I have 3 choices. So out of each end of the branch here, I'm gonna draw 3 more branches, and that's for gray, navy, or magenta pants, and same goes for the rest. Okay, I'm not gonna waste your time here. So here we go. This is basically the description of our possible outcomes and how many other 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 12 here. So a total of 24 different outfits. And notice in the question it said the number. We need to find how many different outfits can we create. We didn't have to list them all. So if we have to list them, then the tree diagram is actually a nice way to organize our options or our outfits But if we don't have to list, but just come up with a number, then we don't have to actually do this tree diagram. But did you notice how this number 24 happened to be? We started with 4 branches, but then for each branch we had 2 more, and then for each of those we had 3 more. So basically we multiplied every time. So we started with 1 point, and then we multiplied it by 4 branches, and then multiplied by 2, and then multiplied by 3. And when you multiply all of these numbers, you will get 24. So basically, in order to figure out how many outcomes we have in total, you just need to multiply the number of outcomes for each selection or for each choice that we made. And this is called the fundamental counting principle or counting rule. Let's take a look at it. So for the fundamental counting rule, it says for a sequence of 2 events in which the first event can occur m ways and the second event can occur n ways, the events together can occur a total of m times n ways. And that's a fundamental counting rule, which we're gonna apply for the next couple of problems. So let's take a look at this example. It says a new computer owner creates a password consisting of 2 characters. She randomly selects a letter of the alphabet, the first character, and a digit for the second character. How many different passwords can be created? That's question number 1. Question number 2, what is the probability that her password is K9? So here we are. The first question that we're gonna ask ourselves is how many selections do we make? Well, here we're making 2 selections. She selects a letter for her first character, and she also selects a digit for the second character. Instead of doing the tree diagram like I did before, I'm gonna actually select a blank line that I'm gonna fill in with a number of choices. So that's the number of choices for the first selection and the number of choices for the second selection. Well, what's the number of choices for the first selection? She selects the letter of the alphabet. Well, we have 26 letters in the alphabet, so that's 26. She can make the first selection 26 different ways. Now, the second selection, she selects a digit. So how many choices do we have for a digit? And it so happens that we have 10 different digits. And I know people now are going to ask, digit is 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So there's 9 digit. Well, don't forget about 0. 0 is a digit as well, and that's our 10th digit. So there are a total of 10 digits that she can select from. So that makes a total of 260 different passwords, where the first letter is a letter and the second character is a digit. So 260 altogether. Now, so we just answered the first question in this problem. Let's answer the second question. What is the probability that her password is K9? Well, K9 is only one outcome out of 260, right? So the answer to that probability that she selects K9 is going to be 1 out of 260. So this problem shows how the number of possible outcomes helps us to find probabilities. And the last example in this subtopic that helps us to illustrate the fundamental counting rule is this. How many license plates could be created that have a digit followed by 2 letters followed by 3 digits? So how many selections are we making? So first we're selecting 1 digit, so that's 10 choices, and then followed by 2 letters, so 1, 2, and for each letter we have 26 options, okay, followed by 3 digits, so 1, 2, 3. And for each selection we have 10 options, 10 outcomes. Okay, so that's what we have. When we multiply those outcomes, those numbers of outcomes, we have 26 squared multiplied by 10 to the 4th power. That's gonna end up, that is a 6,760,000 different license plates. So imagine a tree diagram for this problem. Aren't you glad we don't have to actually do a tree diagram and we could just use the number of choices? Okay, so this is actually how the license plates are selected and the number of license plates figured out. With the exception, they make adjustments for the letter combinations that might be offensive in some languages, so they take out those, but roughly this is how they calculate the number of plates that could be selected with a certain combination of letters and digits. And I'll see you guys in the next video.